the guest lecture by Professor Sheng Wang from Shanghai Jiaotong University will be about visual serving. Visual serving is a quite popular topic in robotics, has been for a long time a quite popular topic. It's an unsolved problem when you go to open-ended or uncalibrated environments. So we are very interested and we look forward Sheng's presentation. Also, Sheng is a researcher very active in this field, in particular in soft robotics, for visual serving with soft robots. And I want to mention that he is the program chair of the upcoming IEEE Robio conference in Bali in a matter of weeks. Okay. Sheng, the floor is yours.
Okay, thank you, Fabio. So today I will talk something about the video serving in uncalibrated environment. I'm Servoing Wang from Shanghai Jiaotong University, and I'm very proud that since the beginning of the Shanghai lecture, I have been involved that. So since the first day I am come to SCTU, so and this year, so I will give a topic on the research I have been done for many years. And the Rob test mentioned to me I should provide more basic knowledge, so I will try to explain word by word the title of my talk. So visual, I think everyone knows what's the meaning of this, so you should use the information provided by camera or other video sensor. Serving is actually a very new word, so it comes from server, and it's a Greek word that means slave. So people want to, the system listen what they want. So they want this, so they create this word slave. So that means that we can perform this, what's the meaning of the command of the human. So uncalibrated means that the environment is unstructured. So you don't have the exact model of the environment, or the environment may changing dynamically. So uncalibrated environment is important if you want a robot work in environment that will dynamic changing, is not fixed. So this topic for video serving have been studied for decades, and since the beginning of the 1970s, the camera have been involved in the industry show. And since late 1980s, the camera became cheaper and cheaper, so more robots will equip camera on the system. So the serving become more popular. Okay, my computer is too slow. So the outline is that today I will first give a brief introduction of the video serving, and then I will talk about the depth independent detection matrix, which is very important for the uncalibrated video serving. And we talk about the video serving problem, and we will talk about also some with some common features, and also the soft robot we are doing recently, and also we will talk about some checking problem, and finally I will conclude my work. So the upper image show about how our human, this is the eye of our human, allow us to receive the image from the nature. So basically, if for our human being, we just some light will reflect from the object, go through the pupil, then go to the retina of our eyeball. Then we can have the image. Of course, they involved of a lot of nature, neuroscience, and some other technology. So according to this phenomenon, then I think the first camera was built in Germany in 18 some which year, I forgot the detail year. So then the camera also have the similar phenomenon with our eyeball. So then people, according to that, they build the camera which could be used like the CCD or CMOS to capture the image of the light reflected by the object. So in the 3D environment, we have suppose we have a point. Then this point will project to the retainer, or we use CCD or CMOS through the optical center. Then this image will be reflected from the camera. Then from this sensor, then we can read this information. And this is from the perspective projection. Of course, we have different kind of projection, but this one is most common one. And if we want to use this information, that means the pixel information of the projection of the 3D point, we have to set up the relationship between the image we obtained and the original 3D point. So we have some equation or some mathematical equation to describe this relationship. And if you want to successfully find this relationship, you have to calibrate this camera. So that means you have to find all these parameters which can describe all this projection relationship. And also the calibration actually is very tedious. You have to, with some tool, of course you can have some calibration bulb, and you should use some other measurement instrument, and then you do with some particular method to calibrate the parameters of its camera. Then after you doing that, you can use the information to do some matching. Still, this we call the intrinsic parameters. Then, if you want to use this information from the image space to the word space, which is very important if you want this robot can move according to the information you have. So we should build a little some frame, such as the camera frame, which will reflect what's the projection and what's the 3D point. And then you should match the 3D point to the camera frame, which we call the intrinsic parameters. So this means the relationship between the camera and the point, which is also very important. And if the environment is unknown, this information will be very difficult to obtain, especially when you have only one camera in your system. Certainly, you can use two cameras to do the 3D construction. A lot of people involve this. However, the 3D the construction, I will show the problem when you use 3D, like the upper right image. This shows that with two cameras, you can recover the 3D information of a particular point of the environment. However, if you want to recover this information, you need the relationship between two cameras. That means the translation and the rotation information of these two cameras, and also you need to know the corresponding point. That means in the left image, which point is corresponding to the image in the left camera, which is very difficult for the information processing. So that means if you mismatch these 2 points, this pair of the corresponding point, you will reconstruct with very wrong or is incorrect 3D position. So which will cause some problem if you want to use this information. So that's why the 3D reconstruction is not rarely used in robotic control. So basically, usually we just use one camera to do the control, not only two camera. So, but if you want to use one camera, we have some problem that we don't know the depth information, such as for our human being, if you close one eye, you try to reach an object in front of you, you may mismatch or not accurately. Of course, we have some pre-stored knowledge so that we have the roughly idea what the depth may be, so we can try to that. But originally, if you have only one eye, you try to do something, you will miss about the depth information. So that's why I think the most creature in the world, they have two eyes. Of course, we have two eyes, so we can know the 3D precision, but we have only a sense of this precision. We don't know exactly how accurate, like how many meters is away from us. And some creature, if you think about the nature, some creature like bird, they have two eyes, but for these two eyes and some fish, they don't form this correspondence. So each eye just in charge of one side of his human body. So how could they swim or move during the motion in the nature? So actually, they're doing this by motion. So when they move, their image will form some optic flow in their eyes. So they will have the relative distance, how far this obstacle and other things away from them, so they can swim or they can fly very easily. So that's what's the problem of if you have two cameras. So you have to deal with a lot of correspondence issue and a lot of calibration issue. So that's why I think that's why the reason the 3D camera is still not widely used in the robotics area. And also, of course, it costs more money and you need much more communication and calculation to do with 3D construction. So back to video serving. So by the definition, video serving is to control the motion of the robot. I use the information provided by video sensor. So basically, three disciplines will involved in video serving. The one is that control, of course, because serving is control. That's the meaning of this word. And another is you use video sensor, so you need some knowledge of the computer vision. And also we should use, we also involve the robots in this term. And nothing, can you play video zero? So in this animation, so we show about what video serving really means. That I think the video is not so clear. Nathan, can you play in a big screen? It seems it's very small. I don't know. Nathan, can you change the video to a very big screen? Okay, that's the biggest you can. Okay, anyway, so this means that if you see the lower left, can you play that again? If you see the lower left, we have the desired image of some shape like a triangle or circle or something, which is previously stored. This is the current image we got, and you also see some black mark, which is pre-stored. The video theory means that from the image plan, we will describe the image, what the current image is, and what's the desired one. You should give the robot or the computer what's the desired one. Then they will have the current one. When they do the matching between the current and the desired, so this will have the error of this image. Then the idea is to control this error to zero. So the desired one will match to the image one will match to the desired one. So when these two images match in the 3D space, the robot will match some particular position if you have enough image. So that's what basically video serving is doing. So according to we have different methods to catalog what kind of video stream we have. One important thing is according to how many cameras you involved and how to use this feedback information, we can divide to position-based image video serving, position-based video serving, and image-based video serving. For the position-based video serving, we have to recover the 3D information of this object or the environment first. So usually people will involve with 2 cameras, then they do the 3D reconstruction. Or people use only 1 camera with some laser or other sensor to recover the depth information. So combined with the depth and the image information, they will recover the 3D information of the world. All the Kinect sensors or some other RGBD sensors. So basically, you should have the 3D information first. Then you feedback the 3D information to your controller, and you have also the desired 3D information. Then you can do the feedback control to let the robot go to the desired position. For the image-based video serving, we only have the image information. That's we have the desired image and the current image. So what we're trying to do is, as we see in the animation, is to control the robot motion so that the current image will go to the desired one, so that this in the image plan, this desired one and the current image will match to each other. As I mentioned about the drawback and the advantage and disadvantage of the position and the image-based video serving. So for the research, most people only involved with image-based video serving. And also according to the camera position and the configuration between the camera and the robot, we can categorize to eye-in-hand or fixed camera configuration. For eye-in-hand, it means that we have the camera mount on the effector of this robot. So the camera will provide the information of the environment to the robot. And another configuration is that we fix camera on other parts or on the environment. So this camera will monitor the motion of this robot. For different configuration, we have different applications according to which configuration and which application you want. And also, according to the information we have, we can also catalog to the kinematic space or dynamic video serving. For the kinematic space, which means that we have 2 loops, basically. One loop is the inner loop, which is in charge of the velocity control of the robot. And this inner loop should provide the velocity control. If you give a desired velocity, the inner loop will control the robot so they will have the velocity you want. And then for the outer loop controller, so they will use the information provided by the camera. Then they use this information to output with some velocity command. And for the dynamic video serving, we have only 1 loop. So that means we consider all the top level. So from the feedback of the camera, then you will directly design the controller from the top level, then you control the robot. So which can the advantage of this dynamic video serving is that we can prefer much faster speed because it's only 1 loop involved and its controller is directly designed in the top level. So we have mentioned some definition of the uncalibrated and what's the meaning of video serving. So there's some challenge if you want to do the uncalibrated video serving. One reason is that if the camera is uncalibrated, you have a lot of parameters, which is unknown. How you estimate these parameters is one issue. And another thing is the depth. So since we only adopt 1 camera, so the depth is changing when the camera or the object is moving. So how you can estimate the depth is another key issue. And of course, we involved a lot of control issue. So the objective I want to this talk we want to derive some dynamic controller which can solve the problem of the intrinsic and intrinsic parameters of the camera, and also the geometry parameters of the features, and also some other issues. So I will briefly introduce our idea is that we introduce some interaction matrix. What's interaction matrix mean? It's a mapping between two velocity space. Because if you want to design controller, usually you will have to design at least at the velocity level. So we want to match the velocity between the image velocity and the Cartesian space velocity. If we finish the mapping, then from the image information, then we can feed back to the Cartesian space. Then you can use this information for the robot control. And then we will try to derive some adapt controller to combine to online estimation all these parameters, which is missing, and also involve some controller design. I will not discuss so much. So this is depth-independent interaction matrix. So I will not go through the detailed information of these equations. So the basic meaning is that if you do the mapping between the 3D space to the image space, you will have the depth information, like the first equation. You will have the depth information in the dominant part of this projection. So which one is time varying? So that means it's changed during when the time goes through. So it will change a lot. So how to deal with this mapping? So in our controller, we will ignore this depth part, and we will compensate this in our controller design. Then we will have a lot of linearization term. Then we can simplify the question. So I will not go through the equations. So another idea is that we use structure for motion. That means during the motion of the robot or the moving object, we can capture a series of the image. From this image is what we read from the camera sensor, and also from the estimate parameters, we can also calculate the estimate one. So if we do the matching between the method one and the estimate one, then we can estimate this parameter online. So the general idea, we can find from the structure for motion in computer vision. I will also not go through much detail about this. So after we combine with the parameter estimation and then the compensator terms, then we can design a control law to do with visual serving. So Nathan, can you play the video one? So this is a very old experiment we did that. So we mount the camera on the effector of this robot. So in the screen we have a desired one, so you can see the behavior. So we only give the command of the desired one and the current one. So what this robot is doing is to control the motion of the robot so that it can match the desired one with the current one. So it moves so fast. So you can see the blue dot, they will converge to the square. In this case, we don't know where this 3D point is. We also do not know where the camera parameters are, what the camera parameters are. So I think so this experiment is using with point. So as we know, in the nature we have many features. We have the point, we also have some line, we have some curve, we have some texture, we have a lot of features which can be used in the feature, and also we have some color or something. So when you do visual theory, most people just involved with point because point is very simple, and somehow point is easy to trace. And also, if you observe the nature, we also have some point, some corner or something you can use for the feature. So point is widely used. However, when we want to extension our feature to most general case. So we try to analyze what we have and analyze the result we obtained. So we extend our method to much more general features. So we found that if an image coordinate can be defined by the shape of this, and which could be any feature, as long as you find any feature which can be described like the formula in this equation. And also we give two necessary conditions. I will skip this. If this feature satisfies this condition, then we can similar method we can serving these features. So these common features, we try a lot of features. I list a few features which we proved which can be used in our method, such as point and line. So we also know line is also quite common, and also some distance, some angles and area and so on. So when we analyze these different features, and the most important thing is how we do the matching between these features to the formula we already have. So take an example for the lower right, we use a line. So usually if you define a line in the 3D space, you will define with a 3D point and a direction vector, which vector will point to a direction. So with these 6 parameters, of course, you can define a 3D line. And when this 3D line project to the image, we will have the 2D line. So you can have also similar, you can have the 2D point with the 2D direction vector. So, but however, when you use these parameters, it's very hard to transform to the formula we have. So we use a new method. So to present the line in the image, so we use a plane vector which formed by the optical center and the image line. This a point and line will form a plane, right? So then we use the unit vector of this plane. We use this vector to present the image line. Then we can use our method to do with the video serving. So I will not go through the details. So Nathan, can you play the next video? So it's also the video we will demonstrate how this line will evolve in the video serving. So you can see that we have a desired line and the current line. So in this figure, the only information we use is a line feature. Also the camera and where the line is, we don't know. We only have the image information. So beyond to that, we also we also extend our feature to the curve features. And also we have the similar situation. We have the 3D curve. I think curve is much more common, since if you see a bottle of water, if the light changing a lot, the curve is also very easily you can get from the computer vision or something, even the light or something change. The curve is also very easily to get. So we want to use the curve to do the video serving. So the similar, we have the 3D curve. Then we have the desired one. So the desired curve, then the mission is how to convert the desired one to the current image. So I will also skip the equation. So basically the idea is we try to find a method to present this curve which can satisfy the two conditions we mentioned. Then we use the similar method we can achieve the target. So Nathan, can you play the next video? So in this video, we have also similar in the image plan. We give the desired curve, and the robot will drive to the desired position. The camera will drive the robot to the desired position. So the desired curve and the current curve will match to each other. Okay, so next, okay, you can see the movie again. So basically, we also do not know where this 3D curve is and where the camera is. So next, we are trying to apply our algorithm to the soft robot, which Rolf is very interested about. So the soft robot is a little different from what's the general traditional robot we think. So the general manipulator is composed by some rigid object. So each joint will link with each other with a revolute or prismatic joint, and the angle between these two joints can be easily measured by the encoders. And however, if you have the soft robot, it's very hard to measure the angle of each joint. And also, because they have the infinity degree of freedom, it's very hard if you want to calculate from the different angle. And also, most of the soft robot is used carbon driven. So that means you use some cable to drive this soft robot. So you don't have such encoder in your system. So usually you only can measure what's the change, the length change of the cable. So in order to build the relationship between the tape of the soft robot and the changing of the cable, so we have to build a kinematics relationship. Then to do that, we use some method. I will not go through the detail, but the general idea is we assume that the curvature is constantly. Then we use some approximation and to calculate, to estimate the relationship between the tape of this soft robot and also and with the changing of the cable. So the detailed information I will skip. So Nathan, can you play the next video? In this video, we use the camera on top, and so this camera will get the robot, the soft robot, to a particular position. And also this will demonstrate how this soft robot can go through some crowd environment, and it can move with very easily, not like the rigid body is so hard in some environment. So also let's okay. So Nathan, can you play the next video? So in the next video, we embed the endoscope into the soft robot. So the left part is the image provided by the endoscope. So the blue one, the green one is the current image. The red one is the desired one. So the left image is showing how this robot is moving. So we embed the endoscope in the soft robot. We can see this point will converge to the desired one, which is useful because for the soft robots it's very hard to control this position precisely. If we can use some vision-based method, then we can conquer this problem and we can solve some problem, and we can use the vision information for this soft robot. Then we can see if we do some disturbance, it can also converge quickly. Okay, so also we did some other tests. Also in the previous image, previous video, we show that we do not know where this 3D point or the 3D feature is. So we don't know the exact position of the 3D feature, and also we don't do the calibration for the endoscope. So that means you can replace anyone you want. So the method will still work. And also some other situation is that this robot is designed mainly for the medical service. So I already delivered a talk for this medical robot in last Shanghai lecture. So you can see the recorded movie, I guess, from the website. So this two figures show that if this robot will do some surgery or medical task inside the human body, so this soft robot is mainly for the heart surgery. And if they go to this environment, because we use minimum invasive surgery, so it's very small hole, so the surgeon do not have the general idea what this robot is, and the environment is very complicated. they might have many obstacles. So they don't know how where this soft robot is stuck. So in that case, we don't know the length, how the length will change in the environment. So we have other uncalibrated information come here. So Nathan, can you play the next two movies? So the next two movies show about even the length of the software robot is changing. We don't know how big they change. They can still achieve the task. So Nathan? I see the movie is here. So basically, these two movies show about okay, so it's still moving. Okay, so the general idea is that even the length of the software robots is unknown, we still can achieve the video serving task. So next, I will talk about some tracking problem. The previous three slides is only deal with the position control, or only control the position of this robot. So however, in many situations or many applications, we have some requirement to control the tracking. Nathan, can you play the next video? In this video, it shows that if we design some trajectory on the image plan, we want this robot to follow this trajectory. So how we can control that? So this robot will follow, like if you want to do the circle or some special movement. So how? Nathan, I think you played the wrong video. So. Yes, this one. So this one shows that you can define a trajectory on the image plan, then you let the robot to follow you define the trajectory. So which is very common and it's very useful in the industry environment. You want to weld it in and do some tasks in the industry environment. So the method, I will skip most of the methods. So the general idea is that we predict the speed of this robot, and then we combine with the desired speed, and then we do all the compensator or something. Then we can successfully control this with some interesting result. And another interesting topic we are doing is that to tracking the moving robot with camera on the tip of this robot. Nathan, can you play the next video? So this, not the last one. I think we have 12 video. No, not this one. Not this one either. I think you could follow not this one, the number of the No, maybe we skip this. So the general idea is that we tracking a moving object which we don't know how this robot will move. So what we're doing is that we use some observer. We try to estimate the motion of this object. Then we try to control the robot so the robot can follow the motion of the robot. If we want to shoot some target, okay, which there's some kind of we can do with this type. So we will involve. So we try to apply this one to the formation control because we observe that in the nature, a lot of creatures like human, if you do the formation things, we only use the image information. We don't use the position sensor or GPS or something else for the creatures. So what we are trying to do, we use the camera to estimate, with only the camera information, to estimate the motion of the leader. Then the follower will keep the image of the leader still in our image. Then by doing that, you can see they will keep the formation still. So similar, we do not know everything about the environment. We do not know what's happened in the camera. So the camera is also uncalibrated. We don't know where we put the camera is on the top of the robot. We don't know how this leader robot will move. So we don't have the communication. We don't have another thing. We have only the camera sensors. So we use the similar technology. We use some filter, some observer to estimate the motion of the leader. Then we use some controller to do the control. And here is the setup of a system. So basically we use two kinds of camera. One is the regular perspective projection camera. That's what we see. That's what our human will do that. And also we will use omnidirection camera. That's this camera you can have the 360 degree of the view. So Nathan, can you play this video? I guess yeah. So in this video, we show about how this robot. This is the omnidirection camera. This video show how this robot, the camera, will see. So we have the desired red one, then we have the current green one. So this robot will try to follow what the leader is leaving. So the follower is continue moving to checking the trace of this leader. And we have a different route. So this one is only the line. Of course, the image recognition still have some issue because if you use omnidirection camera, the resolution of the camera will degrade a lot. So this is doing with circle trajectory. So in this motion, so the leader is doing the circle motion, and the follower is trying to follow with the trajectory what the leader is performing. And also we did a lot of other trajectory. I will skip it. So Nathan, can you play the next video or the previous video? I don't know. So another video to, yeah, this one. So this one shows that we use a perspective projection camera. So you can see this is an ordinary camera. So it's similar. In the image, we give the desired and the current one. And you can see the small image is captured from the ceiling camera to show how this robot moves. So this is line tracking. And also we also do the with circle tracking, and also we also did with arbitrary motion capture. So I think I'm running out of time. So also we try to involve with some not only the vision sensor or the force sensor or some other sensor involved. So this one to show about how we combine with the vision sensor and the force sensor to open the door. So it's also uncalibrated. We don't know how this mechanism of this door. So we don't know how this door will be open. So Nathan, can you play this movie? So this movie show about, so we use the camera to find the bar of this door. Then we grab that, then we use the force to try. So we don't know how this trajectory is. So we only feel that, then we can do the motion. So they can automatically open this door, even we don't know any of this mechanism. So also we tried with different mechanism. So like different door and some door. Anyway, so I will conclude my work. So basically I present something about the weather serving and especially uncalibrated things. So we design some position tracking and with some other sensors. So that's basically all end of my talk. So finally, I want to mention about the conference we are organizing. So it's in a beautiful place in Bali, Indonesia. So and the early registration will end by the end of this month. I hope everyone can join us. I guess Fabio will go there, right? So I hope everyone can join.
Yeah, likely. Yeah.
Okay, see you soon then. Yeah. Okay, Fabio. So.
Okay, thank you, Sheng, for the great lecture. So I think we have really time for again one or two questions.
Fabio, can I ask a question? So, just about the general context of this lecture series. So, one of the ideas that we have been looking at, and at the beginning of your talk, you showed a human eye.
Yeah.
Basically, and then you moved to robotics, and then it was mostly about robotics. Now, is there a sense in which you can actually say that by doing the work on visual servoing that you have been, nicely presenting, you can learn something about human vision, about the human visual system, or is this more or less, let's say, engineering work?
I should say it's more engineering work, but still, if you're trying to do with eye in hand with servoing, you will learn much how human, they coordinate their hand with their eye. So you can learn back from, of course you learn how we human do that. Then from the control of that, you will have much understanding how we do that. We are not estimating first, then we do the motion. So we are doing simultaneously to do with eye in hand. So I think we can have better understanding of it. Somehow,
okay.
It's not.
Thank you. Yeah, not very direct, but at some level.
Yeah,
at some level.
Yeah.
Okay, thank you.
Okay, thank you.
Mine is actually a comment that I may already have done last year on a similar presentation. I mean, of course, when you are going to implement a system, you miss some tool. If you would like to be perfectly coherent with the principle of our lectures in the control, for instance, or if you want to implement visual servoing in an unknown environment with a soft manipulator, we have some, I think you agree, we have to do some research work to develop new models if you want to be perfectly Rolfian. What do you think about it?
Yeah, I think you make a good point. So I also discussed with Rolf for several times. Rolf don't like modeling. So I think so. From what I present, that although it's uncalibrated, we still should have the form of the environment or something. So they do have some modeling involved. So you should have basically a model of what data is. Of course, several parameters or something you don't know, you can estimate, but it's still in all the talk, the method I involved, I need the modeling first. So, but you don't like modeling, I know. So, but still, some people are doing with modeling things, so they do not want to do exactly modeling, but they know the input, they know the output. Like they know the image and they know the motion and they know something by some external sensor or something. So they try to matching the relationship between the input and output with some neuron with some learning or some method. So they do not do the exact modeling as what I'm doing. But still, I think it's the good topic to continue. So if you don't have model or the model it's not what you're thinking, so how you do this. I think that's the good topic and it's worth to do.
Yeah, thank you. Are there other questions or comments from the global hall? So if not, I think we can thank Professor Wang and we can actually close the session. Thank you.